Okay, so we have the last speaker today. It's Sven Buder from Heidelberg, who will talk about detailed classification of stars with machine learning.
Okay, so as you see, I'm going to talk about the detailed classification using, as Ross already introduced, the Canon. Okay, now the computer recognized. All right, yeah, with the Canon. And the Canon is named after this lady who was working in Harvard, and she actually by hand classified about 340,000 stars in her career, which is a lot of stars. But if you actually look at the data that we got from the Gaia satellite, just in this image, you have more than 340,000 stars hidden in there. And if you want to classify all of them by hand, you have more than a lifetime to work with. But the good thing is to answer some of the key questions that we have as galactic archaeologists, like Gregor and me are. You maybe don't need to observe all of these stars, because we want to answer questions like how did the Milky Way actually form and how did it evolve on timescales of billions of years. And the question that I'm particularly very interested in is where are these stars born, and can we find, for example, stellar siblings or even solar siblings? And I know this is a very inaccurate term, but to explain it, we want to figure out if there's some kind of stellar DNA, is there some kind of fingerprint, some pattern in stars or in stellar properties that we can use to link stars that have been born together. And the idea that we have is that possibly chemical composition, so the abundance pattern of stars, might work this way. But the problem is, to actually get these chemical compositions, we only have stars, we only have light from the stars. So as you see here in this picture, you possibly see the galactic plane of the Milky Way. It's basically, if you would look outside in some 7 hours, you might see this. If you actually zoom in, you see a lot of stars. Some of them are clustered together, for example. If you take a picture of this region over a longer period, you see that these stars might move. And from the motion and the position of these stars, you can calculate actually the orbits of these stars. But what you can also do is, if you actually take RGB images of those stars, you can try to somehow organize them by their color. And as Gregor already has shown is, if you put the bluer ones to the left and the redder ones to the right, you get actually a pretty good idea of the temperature of these stars. And on top of that, because we know these stars all belong to a cluster and they are at the same distance, you can actually sort them by their absolute magnitude, their absolute brightness, going from faint stars here to brighter ones here. And you see that these stars follow a really nice pattern, going from stars that have lower masses here, which we call the stellar main sequence, and stars with a higher mass tend to evolve faster and are going to the turn-off region. And then they evolve even further to stars which we call giants. And then there are some stars which are here in the so-called red clump phase, where we have usually a lot more stars. And the great thing is these stars have, for example, usually a quite similar luminosity and also color. So we can use them as some kind of standard candles. And in these clusters, some of the great things is that these stars are born together, so we know they have the same stellar age. So we can use them to estimate the stellar age. However, as I said, the one thing that we're actually interested in is detailed chemical composition. And this we cannot get from just taking pictures. But the great thing is we're actually able to take spectra of these stars. So for example, Gregor has shown similar plots already before. We have some stars that are very hot. And then if we go to cooler temperatures, you see there are some patterns here in these stars that are very characteristic. And these are the patterns that, for example, AnyJump Canon used to classify stars. So hot stars are here, cooler stars are here, and we have some features in those stars that we can use to classify them. Like, for example, hydrogen, but also sodium, some features from other elements, or even molecules. And as I said, AnyJump Canon did that in her whole career, and she classified roughly 50 stars per hour during her career, including sleeping and stuff. So 25 stars in the duration of this talk. But the problem is she did not include the estimation of chemical composition. We actually want to do that. So what we do is we go to higher resolution to not only resolve these small absorption features that you have seen, but we actually observe stars at high resolution in 4 bands. And Gregor has shown this before, because we're both working in the Galar survey where we actually use 4 different bands. So you see here one of those bright features that was one of the hydrogen lines. This is another hydrogen line. And we have those 4 bands that we observe. So this is now a spectrum of the sun, or a solar spectrum. And the sun has, well, a really nice quantity of 1 solar mass. And it has a rough age of 4.5 plus minus billion years. And if the sun would be part of a cluster, the other stars that have the same age and chemical composition would lie on this bluish track here. And the thing is now, if we look at the spectrum of stars with the same age and chemical composition, you will see that these spectra change. So I'm just going along this line here, and you see that these spectra change a lot. But we still want to try to figure out what is their chemical composition. And you see this is a pretty tricky task. And the way we want to do that is, of course, we want to first figure out what influences stellar spectra. And some of those things are actually coming from the stars themselves. So we have some thermodynamic quantities or gradients that basically form the spectrum. Then we have the chemical composition, and as Gregor said before, we, as spectroscopists, we say we have hydrogen, helium, and metals, which also means that carbon and oxygen are metals for us. It sounds a bit weird, but it's quite practical when you actually do spectroscopic analysis. You also have turbulences in the stars going on, and you have sources between the star and the telescope, some interstellar medium, dust, etc. And then also you have your telescope that you observe with. So the telescope that we're using is in Australia, on the other side from here. And you have some stuff like instrument resolution that actually influences the spectrum that you take. And the point I want to make here is that, well, in the first run, what has been done so far is that you try to model stellar spectra by doing something is called spectrum synthesis. So you assume a model, atmosphere model. You do a lot of very difficult things. So, for example, you calculate continuous and line opacities, the radiative transfer. Then you do some chi-square optimization, and then, yeah, it's a very messy business. So in case I lost you here, the actual takeaway is modeling spectral synthesis might be accurate, but it's definitely not easy, even though the spectrum program that we use is called Spectroscopy Made Easy. It's not easy, and also it's very time-consuming. And also you have to be very careful when you analyze these spectra, because when you analyze them, you have a lot of stuff that influences your result. So some of this stuff is, for example, if you look at the spectrum, first of all, we spectroscopists tend to normalize these spectra. But every spectroscopist might possibly set the continuum somewhere differently. You have different parameters going into your estimation. And I think you asked about the quality of line data. That, of course, definitely influences our analysis and the chemical abundances that we get out of our analysis a lot. And also you have, for example, as I show here, where I just show a spectrum of a star. The black points are the actual measurements. And then we have a synthesis of only a calcium line here in red. And then a synthesis which also includes nickel in blue. And you see this line is heavily, like the calcium line is heavily blended by nickel. But you also have a lot of other things going into the spectrum, which are telluric lines or sky lines that you usually have to correct for, which makes everything very tricky. And you end up with some problems that you have to come up with solutions. So one of the problems we faced for the Galar survey was the computational costs, because already now we have observed more than 340,000 spectra. And the problem is if we take the stellar physics-driven analysis, that takes roughly 1 hour per star, doing everything on the fly, and also getting the stellar parameters and the abundances. On the other hand, we need high precision, because if we want to figure out if we can use the chemical composition to tag stars chemically, to basically find stellar siblings, we have to be very precise. So we need a lot of, in the best case, numerous unblinded and well-defined lines. and we actually want to use the whole spectrum if possible. And we came up with the solution of simply combining spectroscopy made easy for a representative set of high-quality spectra with the Canon. And in this case, what I'm going to show you next is actually not model spectra, but this time it's actually observed spectra, because we're actually performing the survey already. So what I'm showing here is basically how the Canon works. So what we do is we try to use linear algebra, which is computationally quite cheap, to construct spectra from stellar labels. And Ross has shown this formula in a similar way, but different. But what we try to do is we try to link the flux that we have here with stellar labels, as I tend to call them, which can be temperature, metallicity, or whatever you want. And then you have these coefficients. And just to show you what these coefficients look like is you start from a spectrum, from a zeroth order spectrum, which is a median spectrum of your survey. And then, for example, you change one of the parameters. Let's say you change the surface gravity. Of course, not the whole spectrum changes, but only certain parts of the spectrum change. Only certain parts of the spectrum are sensible to surface gravity. And you can do that not only for this parameter, where you see it's sensible here, for example, for oxygen lines, but you can actually do that with a lot of different properties. Some of these might come from the stars, so some of these might be abundances or the stellar age or mass, but you can actually also take extinction, which is not coming from the star per se, and you can try to map the sensitivity of your spectrum to these parameters. And to show you how that works in the real life, with actual data that we took, so this is basically a similar diagram as I showed you before, where you can think about this is like color, and this is something similar to the luminosity. But what we do is, in the first case, we have our training set spectra, and we have the stellar labels, which we estimated beforehand with classic spectrum synthesis. And then we train these coefficients. We maximize the likelihood of these coefficients. And in the actual test step later on, now we have the best set of coefficients, and then for each of our survey spectra, we try to find the best set of stellar labels. And this is then how it works, and these are now already more than 340,000 points. And each point that I'm showing here took 0.1 second to calculate, to get the stellar parameters and the chemical abundances. And now, of course, as Matthias said, the problem is how well does this whole thing work? And also we, in our survey, we have to validate, validate, and validate. And you can do that by, for example, trying to first of all figure out how well your Canon model, which is shown here in blue, matches the observation, which is shown behind the blue lines in black. And then you can see, okay, the residuals, you actually have to enhance or magnify the residuals by a factor of 5, because the model and the spectrum match very well. But then you can also say, okay, well, the model and observation match well, but do we actually recover our training set parameters well? So we do a lot of self-validation tests and leave-out tests, and we see that, for example, the difference in temperature between the input parameters and the ones that have been recovered by the Canon are in the order of 50 Kelvin for temperature, but also for surface gravity, and they're in an area that we expect. So yes, we have validated, everything works, so we can continue. And of course, this is not the only strength that we have validated our data, but we also have some other strengths. So for example, the Canon reaches better precision because we can actually use the whole pixel information that is there. The other thing is the Canon is rather fast, so you can estimate 340,000, for 340,000 stars you can estimate the stellar parameters and abundances in less than a day, which is better than a whole career, definitely. And also the Canon is as accurate as the training set. And the one thing that I want to elaborate a bit more on is that the Canon coefficients can actually be regularized, masked, or censored. So basically, if you think that you only want to follow the nickel lines, for example, you can allow the Canon only to be sensitive to the regions where you know there are nickel lines. And the last big pro of the Canon is that you can train actually on external information, because the Canon does not care about the origins of the labels for the training set spectra. What does that mean? The great thing is you don't always have to put in spectroscopic parameters, but you can also take, for example, something I would call non-spectroscopic parameters. So as I said, for cluster stars, we know they're all born at the same time, they all have the same age. This is something we can put in. The other thing is also we can put in distances or distance-dependent parameters from the Gaia satellite. And the last thing that is very interesting is we can also include information from astroseismology, because the great thing is stars oscillate. And they do that with certain frequencies, with certain period separations. And astroseismologists can actually extract this information and learn something about the surface gravity of the star. I'm not going into detail because I'm not an astroseismologist, but I'm just saying this is amazing research going on. But because I'm a spectroscopist, what I want to elaborate on is you can also use the Canon, for example, to cross-correlate or cross-correlate surveys. So you can, for example, take survey A, where you have few spectra but with high quality, and you can also have a survey B with many spectra but with lower quality. And even though these spectra might have been obtained at different wavelength regions and also with different setups, so if the telescopes are at different positions, that still works, because the only thing you need is a small overlap between those two surveys so that the Canon can learn how the spectra of the same stars look like from survey A and B. And then you can propagate the information from survey A onto survey B. Just before I'm concluding, there's also other things that you can use the Canon with. So for example, what I'm showing here is normalized spectra of the infrared. So these are 15,000 angstrom or 1.5 micrometers. And I'm showing here spectra of 3 different stars. One with 0.7 solar masses, one with 2.1 solar masses, and one with 3.3 solar masses. And you see only really minor details. But the great thing is if you put the mass into the Canon as a stellar label, what you see here is, again, some of these coefficients. And you see in red is highlighted the coefficient for mass. And you see that here and here, for example, these coefficients are strong. So there's a very strong sensitivity. And then you can go back to your spectrum and actually see, okay, which lines do we have here? And for example, here where there is a really strong coefficient, you see there's a CN band. But also here, for example, there are CO bands. And the great thing is, then you can go back to your understanding of stellar physics and figure out, okay, well, actually carbon and nitrogen abundances, and especially their ratio, correlates with stellar mass and age. Which is something that is very specific for the evolution in at the giant branch. But the great thing is now we can actually use the carbon and nitrogen ratio as a measure for stellar mass and age, which is really important given that we want to do galactic archaeology. So we definitely need the stellar age for most of the research that we're doing. And another thing is that, as I said before, there's a certain area in the color magnitude diagram or in the luminosity color diagram that I showed, which are red clump stars. So these are stars with a helium burning core. And the great thing is, as I said, we can use them as standard candles. But the problem is, up until now, we had a really, really hard time figuring out which stars are actually already in the red clump phase and which of them are still on the red giant phase, just by looking at pictures of them. But the great thing is there has been research done by Keith Hawkins and others where they included information from astroseismology, because astroseismologists, they're actually able to see the difference based on the period separation and the frequency separation. And you see here that with these diagrams, they have a pretty good diagnostic of which stars are actually already helium core burning and which are not yet helium core burning. And the great thing is, as you can see here, with spectroscopic analysis, they can recover the input from astroseismology. So even here you see that astroseismic values can be used as labels, and this also has a physical background that you could discover by just putting in astroseismology. And to give you a bigger picture of why I'm doing this, so as I said, I'm interested in figuring out if we can use the chemical pattern of stars to figure out or to find stellar siblings or solar siblings. And we just have recently been able to actually estimate the abundances of 340,000 stars. And as you see here, they're all labeled by the actual elements. So we have, for example, lithium, we have nickel, we have, for example, europium, and they have a quite different pattern. And the next step is now to actually figure out if our experiment or our hypothesis that we can use chemistry to find stellar siblings works. So this is still work in progress. But what you should take away from this talk is basically that simple ideas, for example, to describe spectra with quadratic functions can help to understand even the most complex connections. Or just basically try simple ideas, maybe it might work and you learn a lot about stellar physics. The other thing is we can use the Canon to analyze spectra both precisely and fast, and we can apply machine learning and identify imprints of stellar labels. Or for all the spectroscopists in the room, the takeaway should be use the Canon. And in case you still don't believe me that spectra are a beautiful thing, I've actually brought the right tools to show you that spectra actually tell you more than 1,000 pictures, because you can look outside and not look into the sun, but close to the sun and see the sun. But if you actually use those glasses, you can take with your eyes spectra of the sun. And once we're all through, I hope you have a beautiful view outside of this window and see a solar spectrum with your own eyes. Thank you.
Thank you. Have any questions for the speaker?
Louise.
Do you do anything in your implementation of the Canon to make sure that it doesn't learn correlations that aren't related to stellar physics but galactic information? Like, for example, if you naively apply it, then elements that generally are correlated in stars, if it's you expect a high abundance of one element, and then you would genuinely expect a high abundance of another element.
Yeah.
A naive application of it could result in that then the Canon would learn that the lines of the second element would give you information on the first. And how do you prevent that sort of thing?
Yeah. So for me that was also very interesting to learn when I applied the Canon the first time, because exactly this happened. Because some of these elements, for example, titanium and scandium or calcium, so some of these elements have rather similar nuclear synthesis channels, and so they trace each other. And what you can do there is, as I said, you can use the Canon in a masked way or censored way. So you basically, if you have a spectrum, and you say you have a nickel line and then you have an iron line, what you can do is you can allow the Canon to only fit the coefficient for, let's say, nickel in this area, and only allow the Canon to fit the coefficient for iron in this area. Because we know where these lines are.
But what about in the cases where you're using the Canon to learn something about stellar physics?
Oh yeah, there you have to make sure what's going on. So I have not done this actively yet. It would be a great exercise to do that and try to figure out if you're overfitting stuff. But I don't know, do you have a practical case where this happened, or?
Not actually, not per se. I've just seen people who have naively applied it and not used masks, and then they get this problem. And I can imagine that then if you were trying to use this to uncover unknown stellar physics, you wouldn't be able to apply such masks because you're finding areas that the spectrum you didn't know had an influence. But how would you actually know that you were just not picking up an unknown correlation that makes sense in terms of galactic evolution rather than individual stellar physics?
Yeah, it's very tricky. The point is just validation, validation, validation. You really have to make sure that the correlation that you find is actually motivated by the stellar physics. Yeah. Sorry.
I wanted to ask about your fitting process, because as I understand it, when you're fitting 30 elements, you actually fit those in separate Canon runs.
Yeah.
With just TEF and log G as your free parameters.
So there are two ways that you can use this. The way that the Canon was first proposed is that you fit everything at the same time. So you have a set of, for example, 7 stellar parameters, or 7 labels, and they're all connected with their individual entries in theta, and you try to fit them all at the same time. But there are other possibilities that you can do. You can, for example, first of all, try to fit 7 labels and then fix them and add an 8th label in a rather more complicated way. We can talk about that later, I would suggest.
Yeah, so I guess my concern with that has been that if you're running the Canon multiple times, you're getting different TEF and log G values from each set of elements you tried to fit. So how do you then at the end decide on what your best values for TEF and log G are?
Yeah, so the way that we use the Canon right now is we take the values from the largest training set. But of course, whenever you run a new set or run a new Canon model, you have to make sure that the new stellar parameters you get are still close enough to the initial values. So this is also another kind of validation that we do to make sure that we still represent and only perturb the labels and not go too far away from the training set. I hope that was understandable. Yeah, okay, thanks.
How feasible it is to extend Canon to be able to apply it to multiple stars at the same time to get common parameters between them? For example, metallicity in a cluster.
I'm not sure if I understand the question right. I mean, what we do is we try to estimate, like, yeah, we have, for example, a training set of 2,000 stars at the same time. So when we optimize these coefficients, we already do that for 7 or 8 labels or 30 labels for 2,000 stars at the same time. So we, in practice, already do that. Or maybe I have misunderstood your question.
Well, I guess I'm wondering if one can extract, when one applies Canon to get parameters of stars, if one can extract parameters of groups of stars as a whole. No, having several spectra at the same time and getting parameters for each of the stars, but also a common parameter between the spectra.
Common parameter. So this is right now not implemented. It would require some rewriting of the code as it is right now. But I'm pretty sure it should be possible. If you just, yeah, it's just another layer that you add there. Yeah, it should be possible.
No further questions. Let's.
Could I just ask? I need those glasses back. I just got them from our outreach department. I'm sorry. I'm very sorry. But I promised them.
Also, you'll see emission lines.
Yeah, from. That's right. Yeah, if you look at the lamps here, you might be able to see those emission lines.
Okay, let's thank the speaker.